Oh, hello everyone. This is a review of matrices and systems of equations. We're going to start with the substitution method for the system shown on the screen. So what we're going to do is replace y in the first equation with the 5x plus 19. Now remember that 5x plus 19 is a binomial, so anything that's more than one term you want to put in parentheses to group it together. This will keep you from just multiplying the negative 5 by the first term. You have to multiply it by the entire binomial. So we're going to distribute that negative 5. And all we need to do is combine like terms and solve for x. So we get x is negative 3. Now for our next step, we're going to find y. So we're going to put the negative x into one of the equations. And I'm going to put it in the second equation because it looks easier to solve for y. So where I have 5 times x plus 19, I'm going to replace that x with negative 3 and solve for y. And I get my solution set. Now we want to check our work, so we're going to plug that back into the first equation. You can plug it into the second equation as well. It should work for both. And it does work here as well. So always check your work when you get done. Right, for our next one, we're going to do the elimination or substitution method. So in this case, we want to multiply one or both equations by a number to eliminate one of the variables. So I'm going to multiply the first equation by 2 and the second one by 3 to eliminate the y's. So we want our coefficients of the variable that we're isolating to be the same but opposite. So after multiplying the first equation and second equation, I'm going to add them together. And then I isolated the variable x. So x is 5. Now we just carry on like we did before. We're going to put that 5 into one of the equations and solve for y. You can solve for x or y first. It doesn't matter which order you do it in. You'll get the same answer, as long as you do the work correctly. So we're going to replace the 5 in the second equation. We're going to replace the x in the second equation with 5 and isolate y. So I got 20 plus 2y equals 18, or 2y equals negative 2, meaning that y is negative 1. Now we want to check our work, so we're going to go back and plug it in. Since I just used the 4x plus 2y equals 18, or the second equation, I'll plug it into the first to make sure it works. Alright, for our next pair, we're going to use Gaussian elimination with row operations. So I'm going to turn this into a matrix. So using our coefficients and our constants, we have a 2 by 3 matrix. And we're going to do row operations to isolate a variable. So we're going to try to make the 4 become a 0. So I'm going to take the first row and multiply it by 4, and the second row multiply it by negative 7. So this will eliminate the x coefficients. So multiplying the first row by 4, we get 28, negative 12, and 152. And the second row we get negative 28, negative 14, and negative 126, and multiplying it by negative 7. Then we're going to add those equations together. Now remember, the first column represented the x coefficients, the second column the y, and the third column is the constants. So this actually represents 0x minus 26y equals 26. So y is negative 1. Now we can go back and plug in, so we're going to back substitute and get our x value. So I'm going back to the first equation, and I'm going to plug in negative 1 for y. And I get my x value, which is 5. So I have my solution set. Don't forget to check, just like you did with the previous problems. Fill it in and see what you get. Make sure it's going to give you the same solution. All right, let's try one that's 3 by 3. So in this case, we have 3 equations and 3 variables. And don't forget, if it's going too fast for you, you can always pause the video. All right, so we're going to change this into a matrix. So I have my coefficient of x, y, and z, and then my constants in the fourth column. So we're going to try to eliminate the 3 in the first column and second row. So I'm going to take row 1 and multiply it by -3 and add it to row 2. And I'm going to put the answer back into row 2 because that's the row I'm trying to make a change in. So by multiplying the first row by -3, I got -3, +9, -15, and -93, and we're going to add that to row 2. And that eliminates the x coordinate in row 2. So I'm going to rewrite my matrix. Now I want to eliminate the 5 in column 1. So I'm going to multiply the first row by -5 and add it to this third row. And then I'm going to add those two rows together. And I get my new row 3. So I'm going to substitute that into row 3 in the matrix. And now I want to eliminate the 16 in column 2. So I'm going to take row 2 and multiply it by -2 and add it to row 3. I'm going to add these together, and that eliminates 2 coefficients in row 3. And that's going to enable me to solve because the first row is the coefficient of x. I have 0x. The first column is the x coefficients. And then the y coefficient was 0. And then the z coefficient is -6. And now I have z. And now all I have to do is back substitute. So I'm going to go back to the matrix, the third row before I eliminated the y. And I had 16y minus 28z equals -160. And we're going to plug in the z value we found and solve for y. Now we're going to substitute back again. And this time I went back to the original equations, equation 1, and I plugged in. I plugged in the y as -3 and the z is 4 and solved for x. So I have my solution set, which is 2, -3, 4. So we have our solution set. And again, you want to go back and check and make sure it works for all 3 equations. It could work for 1 but not the other 2, or it could work for 2 and not the third. So make sure it works for all 3 equations. Next, we're going to find the determinant of a matrix. So then the 2 by 2 matrix is simply AD minus BC, where A is in the position where 2 is, B is 4, C is 6, and D is 5. So we're just going to plug in. And we get -14. Now one way that we use a determinant is to find the inverse of the 2 by 2 matrix. So when we want to find the inverse, we're going to use the formula 1 over the determinant. Then we're going to switch the position of A and D and take the opposite of the B and the C. So in this case we have 1 over -14, replacing A with D and D with A, we have 5, and taking the opposite of B and C, -4, -6, and 2. And then we'll just simplify it. So there's our determinant. So I would memorize that formula. The other options are to use the augmented matrix with an identity matrix and do row operations. It takes you a little longer. Or you can create a system of equations and solve, but that's the hardest way. So I think the easiest way would be to memorize your formula. Okay, so let's go on, and we're going to find, use the inverse to solve a system of equations. So we have our coefficient matrix, which is just the coefficients of x and y. And we have our constant matrix, which are just your constants. Then we have the inverse of the matrix, which we just found. And we're going to solve the system of equations by taking the inverse matrix and multiplying it by the constant matrix. And we get 3, -5. And again, check your answers. So x is 3 and y is -5. Make sure that you plug it back into both equations, and hopefully you get the correct answer. Now we're going to solve the same system of equations using Cramer's rule. So using Cramer's rule, we need the determinant of the coefficient matrix, which we found earlier. We also need the dx. And with dx, it's the same as the coefficient matrix, except you replace the x values with the constants. And then we're just doing AD minus BC again. And then dy is going to be the same matrix, except we're replacing the y coefficients with the constants. And to find x, we just do dx divided by d, which we came out to 3. And for y, we're going to do dy over d, which gave us -5. So we got the same solution. All right, so next we're going to find the determinant of a 3 by 3 matrix. So we're going to use this one. So I'm going to use the first row as staying steady and go column by column. So I'm going to take the first number in the first row, which will be 1, and I'm going to multiply it by the remaining 2 by 2 matrix after we cross out the first row and first column. Now going across the top, we're going to subtract. Remember, it's plus minus plus for the first row. So we keep the first number the same, the second number we take the opposite of, and the third number we keep the same. So now we have the 2 in the middle. So we're going to cross out the first row and second column, and the remaining 4 numbers will be the 2 by 2 matrix that we're going to find the determinant of. Then we're going to add -3 times that 2 by 2 matrix. So we're crossing out the first row and the third column, and we're left with 4, 0, 5, 1. And we're going to find the determinant of that. So now we have it broken down into constants times a 2 by 2 matrix, which we're going to find the determinant of. So going across AD minus BC, we have 1 times 0 times 3 minus 1. -2 times 4 times 3, we're 12 minus 5. And -3 times 4 minus 0, which gives us a determinant of -27. All right. So we're going to use this to solve a system of equations. So here's our system of equations, and our D, determinant of the coefficient matrix, we just found. Now we want to find dx. So again, we're going to use the same matrix we had before, except we're going to replace the coefficients of x with the constants. So in the x column, we have -10, 1, and 13, and everything else is the same. So it's the coefficients of y in the second column and the coefficients of z in the third column. In our second equation, we don't have a y value, so it's just 0 for the coefficient. And then we're going to find that determinant as well. So I worked it out to be 27, which means that we can find x. So x is going to be dx over d, which is -1. Now we need to find at least one more variable so that we can solve for all 3. So let's go about finding the dy determinant. So dy is the same as d, except we replace the y coefficients with the constants. So that would be the second column. And then we're going to find that determinant. And I found it to be negative 81. And we're going to divide that by the determinant of the D matrix. So that came out to be 3 for y. Now from here you could back substitute and solve. But we'll go ahead and find the determinant of the dz matrix. So with dz, we're replacing the coefficients of z with the constants. And then our first column is the x coefficients, and the second column are the y coefficients. So we get negative 135. And again, we're dividing by the determinant of the D matrix, or the coefficient matrix. And we get 5. So we have our solution set, and we can go back and check our work and make sure it works. Next, we're going to find the inverse of a 3 by 3 matrix, and I've augmented it with a 3 by 3 identity matrix. So the original would be just the 3 columns. We're going to do row operations to solve this. So we're going to take row 1 and multiply it by negative 4 and add that to row 2. And we're going to put our answer back into row 2. So that eliminates the 4 in the second row. And we're going to rewrite our matrix. So this is the same process we went through earlier when we were solving a system by using row operations, Gaussian elimination. So we're going to eliminate the 5 next in the first column. So I'm going to multiply the first row by negative 5 and add it to row 3. And I have my new row 3. So I rewrote the matrix again, and now I want to eliminate the negative 9 in row 3. So I'm going to multiply row 2 by 9 and row 3 by 8. And I got 0, 0, negative 27, 4, 9, and negative 8. So our goal here is to get the identity matrix in the first 3 columns. So we're going to move it over. All right, so next we're going to try to eliminate the 13 in row 2. So I'm going to multiply row 2 by 27 and row 3 by 13. And I've eliminated that 13. So I'm rewriting my matrix. All right, so we want to keep going until we have zeros everywhere except on the diagonal. So let's eliminate the negative 3. So I have row 1 times 9 minus row 3. And we're going to put it back into row 1. Okay, so let's rewrite our matrix again. So this time we're going to multiply row 1 by 12 and add it to row 2, which will eliminate the 18. Now, I have zeros in the first 3 columns everywhere except on the diagonal. Now, I can get the diagonal to be 1s by dividing everything by the number in the first 3 columns. So I'm going to divide or multiply by 1 over 108 for the first row. For the second row, I'm going to multiply by negative 1 over 216. And for the third row, divide by negative 27 or multiply by negative 1 over 27. And that will give me 1s in the first 3 columns, which is the identity matrix. In the last 3 columns, we get the inverse. So we have found our inverse by using row operations. All right, let me know if you need any help.